Hello, everyone. My name is Pablo Samuel Castro. I'm a researcher with Google Brain in Montreal. And today I'm going to be talking to you about reinforcement learning and giving a very brief introduction to reinforcement learning. So this lecture will be based on this colab notebook that I wrote, and the link is here, but you should have this link as well in your course materials. Um, and we will be jumping back into this colab later on. But first, I wanted to give you an overview of what reinforcement learning is and some of the mathematical formalisms that we'll be using. So at a very high level, reinforcement learning is this interaction between an agent that's learning how to behave and an environment. So typically, reinforcement learning is used for sequential decision-making problems. So this means that an agent is making action choices multiple times or at multiple steps. This is in contrast with something like image classification, where you get an image and you yield one classification, whether it's a cat or a dog or whatever. In reinforcement learning, an agent makes multiple choices. For instance, in a game like chess, you don't make a single action choice or you don't make a single move and the game is over. You make a sequence of moves and your opponent also makes a sequence of moves. And based on how these moves combine, the game results in one of the two players winning or a draw. So more specifically, an agent interacts with an environment by making action choices. And so after an agent has made an action, the environment will return the next state. So the agent transitions between states, and we'll get into this a little bit later, as well as a numerical reward or cost. And so this numerical reward or cost quantifies how good that action choice was that the agent just made. And the agent is going to use this numerical signal to learn how to optimize or improve its policy so that it maximizes the rewards it receives or minimizes the costs. So to take a very simple example, let's take this 4x4 grid world where we have the agent as this blue circle that's trying to reach this gold star. So immediately we can see that an optimal policy would be to just go right and then all the way down. And by optimal, I mean the shortest path. So we know the agent knows that if it can execute this, it will always receive the gold star. Now in reinforcement learning, we typically don't have something where we have everything immediately in front of us and we can find a policy as quickly as this. We typically are dealing with a system where we don't know where the rewards are or how our actions affect our transitions. So we may know all the different states that we can inhabit and the actions that are available to us, but we don't know how these actions will affect the environment or how it'll affect where we are or where the rewards are. And so the agent in reinforcement learning typically has to explore around the environment to try to find out these things. So for instance, let's say the agent performed these actions in gray and it was able to visit all these cells in white. So at this point, the agent knows a little bit about the environment, but still doesn't know what's happening here in the bottom right in these gray cells. And it may be that the agent found some numerical reward here, this little gold star. And so the agent might decide that this is fine. So now it knows how to get some positive reward, and it's just going to stick to this policy here, which always guarantees that from any of these white states, that it will always get the gold star. And this might be fine, but we know that there's a bigger star over here. And so if the agent sticks to this, it might be missing out on a larger reward. And so we'll come back to this question a little later, which is central to reinforcement learning, and it's this notion of exploration. So before going into that, I want to introduce some of the mathematical formalism that we'll be using. So we typically phrase reinforcement learning problems as Markov decision processes. So these are defined as these 5 tuples where S is a set of states. So in this example, the set of states are the different cells that the agent can be in. A is a set of actions that are available to the agent. So in this example, the agent has 4 actions, up, down, left, and right. P is a function that takes in a state and an action and returns a distribution over next states. So this basically quantifies the dynamics of the environment. So for instance, if the agent is here and takes the right action, P will say that in deterministic systems, it will end up in this cell to the right with probability 1. Some systems might not be deterministic and you might have stochastic transitions, in which case you might have something like taking the right action will result in the agent ending up here with 0.9 probability or 90% of the time, and 10% of the time the agent might remain in its current state. And so obviously stochastic transitions are more complicated because when you're thinking of planning, you have to sort of consider all possible future states when doing your planning. Whereas in deterministic systems, it's a single trajectory given a sequence of actions. R is a function, it's a reward function that given a state and an action will give you this numerical reward or cost that I mentioned previously. And finally, gamma is a discount factor, and we use this one of the reasons we use this is to encourage the agent from not waiting too long before receiving the rewards that it wants to receive. So in this example, for instance, if we didn't have a discount factor, a perfectly fine thing to do would be for the agent to visit every single possible cell before going to the gold star. If we were just summing over the rewards received in a trajectory without any discount factor, as long as the agent reaches the gold star at some point, there's no difference from just taking the optimal path. However, if we include a discount factor where each successive step is discounted by gamma, which is a number between 0 and 1, then if the agent waits too long, that reward will start diminishing. And so the agent is encouraged to find the shortest path. Okay, a behavior policy, which we typically denote using pi, is a mapping from states to a distribution over actions. So deterministic policies would simply say for each state you have one action that you take, as we have drawn out here. But in general, you might have a distribution over actions. So again, a stochastic policy might say from where the agent is right now, you want to take the right action 99% of the time, and 1% of the time you will choose actions randomly. And as we'll see later, this is actually an exploration strategy that is very common. So each policy induces a value function, which we denote as v pi. And what this is saying is basically quantifying how desirable it is to be in a particular state S if we were to follow policy pi from then on and to infinity. And the way this is expressed is via this recurrence, which is known as the Bellman recurrence, where we basically look at the expectation over actions, given that in general our policies can be stochastic. And we're looking at the one-step reward, given that action, plus the discounted expected value of the next state. So again, S prime is drawn from these transition dynamics. Again, a P is given a state and an action will give you a distribution over the next states. And we're looking over those possible next states, what is the value of that next state if we were to follow pi? So again, this is a recurrence because we can see that v pi occurs on the right-hand side and on the left-hand side. And I'm going to add my pointer. And so this recurrence is well defined, and we can actually compute for it. Note that we have the discount factor here, which means that we have the immediate one-step reward, and the future values, we're discounting it by gamma. And so what we're typically interested in is the optimal value function, which we denote as v star. And here note that there's no policy. We're maximizing over actions, but note that v star is occurring on the left-hand side and the right-hand side. And again, this is well defined, and we can actually solve for v star. So given that we have these values, they only tell us how desirable it is to be in a particular state. But we still don't know how to extract a policy from this, or how to behave given, for instance, v star. And so before we introduce how to get the policies, I'll introduce what we know as Q functions, and where v functions take a single state and give you a value or a numerical value for how desirable it is to be in that state. Q functions do something similar, but now you're specifying an action. And this action might actually be different from what the policy would specify for this particular state S. So in this case, for a particular policy pi, what this allows us to do is to evaluate or compare the desirability of taking action A relative to following policy pi. So if we have v pi, you can see we can compute q pi simply by making this what we call a Bellman backup. So taking the immediate reward after following action A, and then looking at the expected values multiplied by the discount gamma. So what we can do is we can then compare for a particular action A what the value of q pi gives us relative to v pi. And if it's something greater than v pi, then this is an indication that perhaps when the agent is at state S, the policy should change to pick action A as opposed to whatever it was picking before. And in v star, because it's optimal, none of the actions will be greater than the value that v star gives us. But what this allows us to measure is how suboptimal an action is, as well as how to extract the optimal policy, right? Because if we have q star, now we can simply figure out what pi star, or the optimal policy, is by taking the argmax over all possible actions. And so with basically, if we have v star, we can then extract q star, and if we have q star, then we can then extract pi star, and now we have the optimal policy for the agent. So this is all fine in the case when you know the full model and you can compute for these values exactly. This is typically known as planning. There's a lot of overlap between planning and reinforcement learning community, and so we're just going to go over one of the possible algorithms for doing planning when the model is known. And what I mean by the model being known is that we have access to the p function, or the transition dynamics function, as well as the r function, which, as I mentioned previously, in reinforcement learning we typically assume we don't. So a very well-known algorithm is value iteration, and this is used to find v star. As I mentioned, if we know v star, we can get q star, and if we know q star, we can get pi star. And so the way it works is that if we have an estimate, say at time step t, our estimate is vt, we can perform this update, which is called the Bellman backup, and get a new estimate vt plus 1. And so what we're doing here is we're finding the action that maximizes the sum of the immediate reward after taking that action, and the discounted sum of expected next values. So here we're replacing the expectation that we had in the previous slide. Here, this expectation, we're replacing it with an explicit summation. So we're looking at all possible next states, looking at the probability of landing in those next states, and then multiplying that by the value, our current value estimate at that next state. And so it's been shown mathematically that as you let t go to infinity, these estimates will converge to v star, which is our optimal value. And so this gives us the value iteration algorithm. We can start from an initial estimate of v, let's say 0 everywhere, and we can just loop until convergence. For each state, we perform this Bellman backup. And because we know it will converge eventually, we can wait until it converges, or until the difference between our estimates gets very small, and then we can return this new v, and this will be either exactly v star or something very, very close to v star. And so a lot of the algorithms that we'll be looking at later are based on this idea of value iteration. So again, reinforcement learning, we are assuming that we don't know the model. So we don't have access to p and r explicitly. And so what we do here is that we have to explore the environment and try to either learn a model explicitly or just learn these values by interacting with the environment. And so back to this example where the agent found this small star here, the agent could just be fine to stay with that policy because it knows it can always get this little reward. But again, it might be missing out on this larger reward here. And so this is a dilemma that the agent faces. Should I explore and potentially find a better reward, but I might also find a very bad state where I get a huge penalty, which I'd want to avoid. So do I want to explore and take this risk, or do I want to simply exploit what I know and just stick to that at the expense of potentially missing out on better rewards? And so this is called the exploration-exploitation dilemma, and there are many strategies for dealing with this. One of the simplest and most used is what's called epsilon gradient. It's very simple. So epsilon is a number between 0 and 1, and so what we're going to do is with probability 1 minus epsilon, and epsilon is typically very close to 0, so it's a small number. So most of the time, we're going to select the action according to whatever our current policy pi is. So whatever pi tells us, most of the time we'll follow that. But with probability epsilon, or some small fraction of the time, we're going to select an action randomly. And so this will allow the agent to explore by picking suboptimal actions, potentially finding better states or better paths to maximize rewards. But also it runs a risk of running into undesirable situations. So if we're in this example, by following some type of exploration strategy, the agent might be able to explore this gray area and eventually find this larger gold star, which then the agent can update its policy so that it reaches the gold, both the small and the large star, as opposed to just the small star. So in reinforcement learning, given that we don't know P and R, we can't do value iteration explicitly. So how can we learn V star and Q star? So one way is using Monte Carlo methods, which I'll discuss now, and that will lead us into Q-learning. And there are many other methods which I won't go into in this talk. So in Monte Carlo methods, the agent will execute its current policy pi and accumulate trajectories by executing this policy pi, and it will also record all the rewards that it receives throughout these trajectories. And then what it'll do after doing this for a while, it'll basically just do an average. So given a state, an action pair SA, its estimates for Q will simply be the average of the returns it receives. And if we're dealing with discount factors, then it'll also include the discount, obviously, in computing this average. And then we update after performing this update for Q, we're going to update the agent's policy pi by simply taking this argmax. So this again is a pretty simple method. It's known to work fairly well. But the issue is that we have to record these full trajectories. So it can be sometimes inefficient, and it can also require more memory than you perhaps would like to have lying around. So Q-learning is a method that's similar to Monte Carlo, but rather than accumulating returns over trajectories, it's going to perform updates for each transition. And this is, for those of you that are familiar with this, is very similar to dynamic programming. And in fact, Richard Bellman, the person who coined the Bellman updates that I mentioned before, is those Bellman updates were where dynamic programming came from. So Q-learning is using this notion of temporal difference. And so what this means is that given a particular reward and next state that we've observed, we can perform this summation here, and note that this is very similar to the Bellman backup that I was mentioning before that we use for value iteration. But this is for a single transition. So we have a single reward R and a single next state S prime. So now what we can do is we can compare this Bellman backup with a single transition to our current estimate of V. Right? So this reward is what we received after executing policy pi from state S for one step and landing in state S prime. So this is our temporal difference. This is basically measuring how different is our current estimate from what we just observed. And so Q-learning uses this temporal difference in this update over here. So if we have our estimates Q and V, we can perform our backup by looking at our current estimate of V at state S and then adding this temporal difference update weighed by a value alpha. So alpha you can think of as a learning rate, right? So this can, if we set it to very small, then our updates, our estimates will change we will have very small changes to Q based on whatever we observe from the environment. And as we make alpha larger, our updates will be more drastic. So the way Q-learning works is as is described here. So we initialize estimate for Q, for instance, just as in value iteration, we might start with everywhere zeros, and we initialize some policy pi, let's say just by picking an action randomly for each state. And we're going to pick a start state S. So while we're still learning, we're going to pick an action A according to pi and any exploratory policy. So what this means is that we may pick the action according to the policy pi with probability 1 minus epsilon, and epsilon % of the time we're going to pick an action randomly. So we're going to send the selected action to the environment. The environment is going to return our next state and a numerical reward or cost. And now we're going to compute the temporal difference error, and we're going to save it in this variable delta. So again, this is R, and we are going to use our current estimate for Q to find basically our current estimate of V star. So we're taking the best action from the next state, and we're going to multiply it by gamma. So this is again the Bellman backup, and we're going to compare it to our current estimate of Q for the current state S and the action we selected A. So again, delta is our temporal difference error. And now we're going to update our estimate for QSA by taking our previous estimate and adding the temporal difference error weighed by alpha. And once we've done this, we can update our policy pi by picking the action that maximizes the Q values. based on our current Q estimate. And now we're going to, because we actually performed an action and the environment returned a new state, we're going to transition to this new state S prime and repeat this process. So basically, the agent isn't moving around in the environment. It's sending actions to the environment. The environment tells it where it landed and says this is the reward or the cost received. The agent updates its Q estimates, updates its policy, and continues interacting with the environment. In certain environments, you might have something like a reset state. So after a while, the environment might send it back to the initial start state, or you might have something where it's just kind of wandering around forever. So this is how Q learning works. It also is known to converge under certain conditions that are fairly mild. And so now I'd like to jump into the Colab notebook and show you how we can actually implement these algorithms and use them in practice. And we're going to eventually be looking at this classic control problem called cart pole, where you have this cart, which is this little black rectangle here, and you have a pole that's sitting on top of it. And so the pole can move left and right, and the agent, what it does is it controls the cart. So it can move the cart to the left or move the cart to the right. And what it's trying to do is maintain the pole balanced on top of it. So it can do this by moving left and right. And for each time step that the pole is balanced upright, the agent receives a reward of 1. And once the pole passes a certain threshold, the angle passes a certain threshold, the game ends. And basically the agent no longer receives any more returns. So let's switch over to the Colab notebook. Okay. So the first thing you will need to do is you will want to click on runtime. We're going to go to change runtime type and make sure that you have GPU selected here, because this will make training happen a lot faster. You can click save and let's click to connect. So we're connecting to a runtime on Google Cloud that will allow us to run all of these examples. So I'm going to skip through the first bit because this is all of the material we just reviewed right now. And so these are the simple examples. These are defining MDPs and policies. So here we're going to start setting up the Colab. In this cell, we're just installing all of the different Python libraries that we're going to need for the Colab. So you don't really need to, if you're interested, you can double click and open and see what I'm installing, but it's not necessary. One thing worth noting is that we're using Dopamine, which is a reinforcement learning research framework that we released about 2 years ago. Another thing worth noting is that we will be using JAX for defining our neural networks once we get into the neural network section. Okay, so we're just going to run this. And you may get some errors as I'm getting there, but it's okay. You can just ignore those. This should work. And so while it's installing that, let's start going through the Colab a bit. So as I said previously, if we have access to P and R, we can compute V star using, for instance, value iteration. There's this other type of algorithm that's very well known that's called policy iteration. And here, instead of updating estimates of V, you're going to be updating your policy directly. So I won't go into policy iteration here, or at least not now. We'll first start with value iteration, which I already introduced, so I'm just going to skip through this part. But we can start looking at code now. So again, I was talking about P and R as functions in a mathematical sense, but you can also express them as objects in code. So for instance, we can have P and R be NumPy arrays, where the shape of P, for instance, is num states, num actions, and num states. So basically, given a state S and an action A, the final dimension gives us the distribution over next states. R, again, given a state S and an action A, the element in that in that position in the array will tell us the reward for performing action A from state S. And we can maintain our V estimates via a vector of dimension num states, and similarly for Q. So we can basically then compute v with 2 lines of NumPy code um, by performing the following. So here we're first obtaining q by summing our one-step rewards, and then doing this multiplication given that we already know v. As I mentioned before, if we know v, we can extract q from v exactly. And then we can update v and continue this process. There's also this einsum function that NumPy has, which I quite like. And this allows you to do the following. So rather than doing this matmul, I like this because it allows me to be explicit about the dimensions. So here I'm saying that P is this three-dimensional matrix, and I can give it letters that correspond to the letters we were using before. So S and T for states and A for actions. V is the value for the next state, so I can use T. And then this is basically telling einsum that these are the dimensions, and so you can see that the T's correspond, and I want you to return a two-dimensional matrix of dimensions S and A. And this will give me the expected next value given that I performed action A from state S, and then I can multiply that by gamma and add it to my one-step reward. So again, once we have V star, we can compute Q star and pi star from that. And so here we have an implementation of value iteration. So value iteration, again, it's a known model. So we're receiving P, we're receiving R, gamma is our discount factor, and we're going to give a tolerance. So basically, as I mentioned, you can either go until convergence, until they're numerically equivalent, or you can iterate in value iteration until the difference between the estimates at successive iterations are below a certain threshold. So basically, they're essentially the same. And so we're going to run this cell so that we have the definition. So here we're just making sure that the shapes of P and R are what we'd expect. We're going to extract the number of states, number of actions, and we're going to initialize V and Q to be everywhere 0. Here we're saying that the error is above our tolerance, just so that this while loop doesn't exit immediately. And so what we'll do is, given our initial estimates, we'll first do the Bellman backup using the einsum that I mentioned before. We're going to have a new value estimate by taking the argmax over Q. And now we can measure the error by simply comparing our new value estimate with our previous value estimate. And again, if this error is below tolerance, then we'll exit the while loop. And so we're going to update our current estimate with the new V, which has been updated using the Bellman backup. And then once we're done with this while loop, we can return our estimates of V and Q. Okay, as I mentioned, there's other methods for finding these value functions. One of them is that's also well known is policy iteration, where instead of iterating over the values, we iterate over policies, and we stop once the policy is no longer changing. So the way it works is that we can initialize our policy pi arbitrarily, so basically choose random actions from all states, and we're going to assume it's simply it's a deterministic policy. So for each state, it's going to pick one action with probability 1. And so as long as pi is changing, we're going to continue updating our policy as follows. So we still have to maintain an implicit estimate of Q, but this isn't what is defining when we stop our loop. So we're going to update Q similarly to before using the Bellman backup. And now we're going to update policy by taking policy pi by taking this argmax. So as soon as pi stops changing, we're going to exit the loop, which this is different than measuring whether Q is changing, because Q might still be changing, but the policy might be stable. So sometimes policy iteration can be faster to converge because it's not so much concerned with exact numerical accuracy, it's more with the behavior policy. And so once we have pi, then we can figure out Q by leveraging our previous estimates of Q, and then we can just extract our V star estimate from this and return that. So again, in contrast to value iteration, we're getting Q star and V star from pi star. And so here we have the definition of policy iteration. Again, we're receiving P and R because this is known model, and gamma. And note we no longer have to specify a tolerance because we're no longer looking at numerical equality. We're looking at policy changes. So whether our policy is changing or not. So similar to before, we start with everywhere 0 estimates. And what we're doing here is we're specifying an initial random policy for each. So for each state, we're going to pick one action randomly, and that will be the initial policy. And so we're going to maintain this variable policy stable that tells us whether our policy is still changing or not. And so we're going to extract v from q. So we have our estimate q. We're going to use our current pi to figure out what our new estimate of v is. And here we're using a Python comprehension where we're looping over all states, and then this array will be, this vector will be fed into v. And q, we can, once we have this estimate of v, we can again use this einsum, use this Bellman backup to obtain a better estimate, a new estimate of q. And then we update pi by picking the action that that q is providing the highest value for. So we're going to determine whether our policy is stable by simply verifying whether our two policies, pi and our previous policy, are equal. If they are, then that means that our policy is stable. And once we exit this loop, then we can extract v and q from pi. So we're doing this sort of two-step thing because for the backup of q, we use v here. So this, once we do this Bellman backup, q might actually induce a different value of v. So that's why we're doing this in this sort of two-step way. And then we return v and q. So this is policy iteration. Again, it's iterating over policies as opposed to values. But again, in reinforcement learning, we don't typically have access to PNR. So what we do is something like Q-learning, which I mentioned before. And so the standard reinforcement learning scenario, as I mentioned, is an agent interacting with an environment by sending an action to the environment, and the environment will return the next state as prime and a reward. Okay, so I mentioned Q-learning, but that is one way of doing reinforcement learning. That's a model-free method because we're maintaining an estimate of Q. As you may have noticed that in no place in the Q-learning algorithm are we actually maintaining an estimate of P and R. So Q-learning is a type of what's called model-free method because we're not maintaining an estimate of the model explicitly. But you can do that, and those are called model-based methods, where we will interact with the environment, accumulate experiences, and then build estimates for P and R, and we'll denote them as P hat and R hat. And once we have these, then we can use some of the methods that I mentioned before, value iteration or policy iteration, because now we have a P and R. Obviously, how good a result we'll get will depend on how good an estimate of P and R we have. So there are different pros and cons for either of these methods. Both are still quite active in the literature today, and they both have extensive lines of research. So just to review a few, model-based methods are typically more sample efficient. And what I mean by this is if you're able to accumulate enough experiences with the environment and you build a model P hat and R hat that is sufficiently accurate, that it represents your system well enough, well, then now you no longer have to interact with the environment, right? You can draw samples, quote unquote, for free from your model, and you can save from interacting with the environment. So this might be quite desirable in systems, in real world systems where it's very expensive to actually interact with the environment. For instance, running a very expensive robot or driving a car in real streets. Those are both very expensive things to do and potentially dangerous. So if you have a very good estimate of your model, then it's easier to do this in simulation. On the other hand, model-free methods are often easier to learn, and we can continuously update our estimates in an online fashion. So the more we interact with the environment, the more we can update our estimates. For the model-based methods, you typically learn a model first, and then you do your planning or your learning to find the optimal policy. So again, there's extensive literature for both. There's no clear winner or loser. For this Colab notebook, we're going to be focusing on model-free methods, but there's literature at the end of the notebook for if you want to explore more. So within model-free methods, there are also two different types of methods that are probably the most well known, and these are value-based versus policy-based approaches. So For value-based methods like Q learning that I introduced previously, we maintain an estimate of the value function or the Q function, and we extract our policy from that. In policy-based methods, we're maintaining and updating an estimate for pi. So as you have probably noticed, this is very akin to the relationship between value iteration and policy iteration, for instance, where in one we're really interested in maintaining accurate estimates of V and Q, whereas in the other one we're more interested in finding a stable policy pi. And again, there's pros and cons for both. There's extensive literature for both. There are hybrid methods that try to use both methods, but in this notebook we're going to be focusing on value-based methods. And so there's extensive literature and there's extensive educational material for policy-based methods if you're interested in finding out more. This is a good point to mention the Sutton and Bartow book, which is linked in the Colab notebook. This is probably the most well-known resource for reinforcement learning. It's the canonical textbook on reinforcement learning, so I highly, highly recommend it. It's very well written. But for policy-based methods, there's also this blog post by OpenAI called "Spinning Up in Deep RL." That's also quite good, and it goes through a lot of the details in depth, and it's a bit more interactive, so you can read it on the web and play around with the code they provide. Okay, so for the rest of the notebook, again, we're going to be focusing on value-based methods. I briefly mentioned this previously, exploration. It's one of the central aspects of reinforcement learning. As I mentioned, if an agent finds some type of numerical reward, if it were purely exploitative, it might remain with that policy and receiving that small numerical reward forever. But if it wanted to explore a bit more, it might find better rewards to receive, but there's also risk that it will fall into some undesirable regions of the state space, and maybe it's irrecoverable to come out from those. So it's a risk that the agent has to take to balance this exploration exploitation trade-off. This area of reinforcement learning has a very, very active research community. There's a lot of work coming out. This has been active for many, many years. There are many different types of exploration policies. Some are more useful for certain types of environments. Some have more theoretical properties than others. It's still kind of an open question what the best is, and it often depends on what you're interested in. If it's more of a theoretical grounding, certain methods will be more applicable. If you're interested in risk-averse learning, then there are other types of exploratory strategies you can use. So what the central point here is that it might benefit the agent to occasionally pick a suboptimal action. So an action that appears, according to the agent's current estimate, appears to be less optimal or less desirable than its current policy says, but we're picking it to sort of find out whether it produces something better. So to make an analogy with the real world, for instance, if you move to a new city and you find a route to take if you're biking from your house to your job, you find this nice route and you know it takes you there in, let's say, 30 minutes. And that's fine. But let's say one day you feel a little exploratory, and so you take this other route. Well, it might be that other route was actually pretty bad and it took you an hour and a half to get there. Now you know to avoid that route. But it might be that route was actually a shortcut and you got there in half the time. You got there in 15 minutes. Well, exploration paid off and you found a better policy. So it can help to be exploratory, but also you don't want to be purely exploratory. Because if you are always exploring, you'll never converge into a stable policy. And you'll always be trying new things, which maybe is okay. But it's hard to guarantee that you will be able to receive a certain amount of reward every time you interact with the environment, which often is what we want from these agents. We want them to be able to maximize the sum of these numerical rewards so that we can perform a task optimally. So this balancing of the exploration-exploitation trade-off is a very active area of research. Epsilon greedy, which I introduced previously, is probably the most well-known, probably the simplest of the exploration strategies, and it's still used in many of the most popular algorithms today, in large part because of its simplicity, in both implementation and in understanding, and also because typically when you're doing research and you're trying to introduce a new algorithm, if it doesn't have to do explicitly with exploration, it's a simple baseline to stabilize the comparison with other agents. Sorry, just need some water. Again, epsilon greedy exploration will select an action randomly with probability epsilon. So epsilon is typically a small value. And with probability 1 minus epsilon, we'll select according to your current policy. So there's more sophisticated versions of epsilon greedy where you don't maintain epsilon fixed throughout. So for instance, you might start with epsilon being 1, which means that you'll always pick actions randomly. And you sort of decay that epsilon value as you interact with the environment. So what that means is that you start with a purely exploratory strategy, which means just pick actions randomly and you're just trying to gather as much information from the environment as possible. And as time progresses and you assume that the agent knows more about the environment, you decay epsilon so as to start switching more towards a more exploitative policy and starting to produce more stable and predictable behaviors. So epsilon greedy, as I mentioned, is very simple. It's very easy to implement. We're going to run this cell. Here's an implementation of epsilon greedy. So the way it works is we'll pass in a state, our current policy pi, and the epsilon value used for epsilon greedy. So we're going to flip a coin, and if that coin is below epsilon, then we're going to choose an action randomly. Otherwise, we're going to choose an action according to our policy pi. And this, again, is using NumPy, which I assume most of you are familiar with. Okay, so as I mentioned, there are different ways in the initial introduction. There are different ways of learning how to behave and how to update these estimates. One way is using Monte Carlo methods. And as I'm going to go over the algorithm again, so we start with an initial estimate of Q, pick some start state S, and we're going to initialize a list of returns. So this, for each state and action pair, it's going to accumulate the observed returns from each state, given that we follow whatever our initial our policy pi is doing. So we're going to initialize our current policy randomly. And so while we are learning, we're going to generate a trajectory as follows. So we start from S0. We'll pick action A0 according to our policy. The environment will give us a reward and a next state. And from that next state, we'll again pick our actions according to pi and continue in this way to accumulate this trajectory. Now we're going to use this variable g, which will be our accumulated returns. And so we're going to start from the end of our trajectory and go backwards. And so what this is doing is it's simply saying adding the returns in reverse. And by doing so, we're going to be introducing this discount factor that I mentioned previously. So what this will result in is that the initial reward we receive here will be undiscounted, and the reward we receive in the first step will be discounted by gamma, and the reward we receive in RT will be discounted by gamma to the power of t. So if our current at time step t, if this pair STAT does not appear in the trajectory beforehand, then we're going to append this accumulated return g into our list of returns for this particular state action pair. Now, the reason we're doing this is because when you're executing a trajectory, you might have loops. So an agent might return back to a state that it had visited before, and it will may pick the same action because of the policy. So we don't want to do this double counting. So we're going to find the first occurrence. So if we were to go forward and we're looking at STAT, we're going to want to find the first occurrence of that state action pair and look at the returns from then onwards. And so this is what this if statement is doing here. And so once we've done that and we've appended G to our list of returns, again, we're going to be executing these trajectories multiple times. Then our estimate for Q is simply the average of these returns. And again, as I mentioned previously, we have the discount factor embedded into the returns that we're appending to our list. So once we have our estimate of Q, we can extract pi by simply doing the argmax. And so the next code cell implements this. This will be Monte Carlo. Now we're dealing with the situation in reinforcement learning where we don't have access to the model. So we are not passing in P and R as we were doing before for value iteration. We're passing in the number of states, the number of actions, and a step function. So this step function is a function that's going to receive a state in action, and it will return a reward and the next state. And so we have gamma, which is our discount factor. We're going to specify a start state. So in some situations, we'll want to reset the environment. So that's why we specify a start state. And this reset state basically says if you reach the state, you want to, again, return to the start state. So for instance, in goal-directed environments, like when you want to reach the star, once you reach the star, you might want to say, okay, start again. Or if in some game where there's like a game over, once you reach game over, then you get to start again. We also specify the total episodes. So this is how many of these trajectory accumulating episodes we want to run. Another common parameter is max steps per iteration. So this means when we're executing a trajectory, we may want to set a cap on how long that trajectory is, because some trajectories might never end. The agent might be just looping forever. And so to avoid these types of infinite loops, we'll set a maximum, the epsilon for our epsilon greedy, and our current estimate of V. This is the ground truth V star. The reason we're passing it in here, it's not really cheating. It's just so that we can accumulate, we can measure how well we're doing relative to the ground truth, and we're going to accumulate this in an array, and we're going to use this for plotting later on. So what this method will return is our estimate V hat, Q hat, and the errors as measured relative to this ground truth that I just mentioned. So we'll look at the maximum of the error, so the state that has the worst error, and the average overall states of the errors. So the way this works is we'll initialize our policy randomly by picking an action. For each state, we'll pick one action that it will choose. We'll initialize Q randomly, and this returns is the G that I was mentioning when I was describing the Monte Carlo algorithm. We're going to want to also maintain counts because we're doing averages. So we want to see how many times we've added to the list of returns so that we can normalize it. And then we're basically going to iterate over the episodes, initialize to a start state, and then we'll execute this trajectory. Again, we'll do this up to a maximum that we've specified. We're going to pick actions using our epsilon greedy strategy. And again, this step function is basically how we interact with the environment. So we'll specify a state S and an action A, and it will return a reward and the next state. Okay. And so now once we've accumulated these trajectories, we're going to update G by going in reverse. So starting from the last state, and we go backwards. We accumulate G and add it to multiply it by the discount factor, so we have this discounted sum of rewards, and this is the basically implementing that if statement that I mentioned above, where we only want to look at the initial occurrence for each state and action pair to avoid double counting. And now we're going to add G to our list of returns, and we're going to update our counts. Q will be simply the average of the returns, and pi hat will be doing the argmax over our current estimate Q. So we continue doing this until we've done enough episodes, the episodes that we specified, and then once we're done, we'll return our current estimates of V, Q, and you can see here we're measuring the errors of our current estimate V hat relative to the ground truth V, and we'll be returning that. Okay, so I think I ran this already, but we'll run it again. Okay, so as I mentioned, Monte Carlo updates our estimates by interacting with the environment, but it requires doing these updates of full trajectories. So Q-learning is nice because it can perform these updates after each transition using temporal difference. So again, the temporal difference is the difference between the reward plus the discounted value of the next state that we just observed given the current transition, compared against our current estimate. And so this temporal difference will weigh it by a learning rate alpha, and we'll add it to our previous estimate. So again, alpha, just like epsilon that I mentioned before, can have a schedule, so we can decay alpha, so that initially we might want to update more aggressively, and as we interact more and more with the environment, we might want to make these updates less drastic. And so we can anneal alpha as we interact with the environment. But in this simplified setting, we're going to maintain alpha constant throughout, similarly with epsilon. So the way Q-learning works, again, is we pick an action according to our current estimate pi, and any exploratory policy we may have. We send it to the environment, receive our next state S prime and R, compute the temporal difference error, and then update our Q estimates using the weighed temporal difference error, where it's weighed by alpha. And then update our policy and continue iterating this way. So here we have an implementation of Q-learning. Again, this is the same signature of the function as for Monte Carlo. So we give it the number of states, the number of actions, a step function to interact with the environment, the discount factor gamma, the start state, the reset state. So reset state, again, is when we reach that state, we're going to want to reset back to the start state. The total episodes, the limit for how long a trajectory can be, epsilon for epsilon greedy exploration, alpha, this is the step size or the learning rate for Q-learning, and the ground truth V to measure our errors. So again, we start with a random initial policy where for each state, we'll pick one random action. We start with Q everywhere 0. And for the number of episodes we specified, we're going to initialize our state to the start state. And now we're going to interact with the environment for a maximum number of steps. We'll pick our action according to our epsilon greedy strategy. We'll interact with the environment by sending that action from that state, receive the next state S2 and the reward. We compute the temporal difference error and update our estimate of Q using this temporal difference error. We're going to be this cumulative return. This is just for plotting, so we're not actually using this in the learning process, but we'll be generating plots for how well our agent is doing as it interacts with the environment. And then we're going to update pi hat using our new estimate of Q. We update our current state to whatever the next state we transition to and continue in this way. So if we ever reach the reset state, we'll just return back to the start state. And then finally, we're going to compute these statistics, so how well the agent did in this particular episode, and we'll measure the errors of our estimate V hat relative to the ground truth V. So I'll run this again. Okay. So now that we have all the code for implementing these algorithms that we just discussed, we're going to start by evaluating them on a very simple example. This is a chain MDP, which we have here. I'm going to run this again just so we have the definitions. So the way this works, can't see all of it, is you have this series of states S0 through, in this case, S6. So I've provided this form so you can play around with this. So just to make it smaller, it might fit better this way. Oh no, it still doesn't. So you can change the parameters, but basically it's a chain. So you can see S0 to S4. There's two actions, the blue action, which corresponds to moving right, and the left action, which corresponds to moving to the left. In the middle of this chain, no matter what action you take, you're going to receive a reward of -1. If you're in the start state, S0, you can choose to take the red action, receive a reward of 0, and go to the sync state where you're done. But you might also want to move along this chain and accumulate these negative rewards. But once you reach the end, if you perform the right action, you're going to get a very big reward. So the longer the chain is, we're going to put it back to 7, just because that makes it a bit more challenging for the agent. The longer the chain is, the longer it has to wait and receive these penalties before it can receive this large reward. So you can play around with the small reward is whatever the agent receives when it just simply goes to the sync from the start state, and the large reward is what it receives at the end of the chain if it goes to the right. And playing around with these values will change the dynamics. You can also play with the penalty, so whatever it receives in the middle of the chain. So the first thing we're going to do is we're going to compute Q star and V star with value iteration. Again, here we're providing the transition dynamics to the system directly. So we are going to do that. Now, this value rho is a slippage probability. So as I mentioned, there is you can have stochastic transitions. So what this is saying is rho says with what probability will the agent stay in the same state. So if the agent right now it has a rho of 0.1, we're going to run this to compute Q star and V star with value iteration. So that means that if you take the right action, you'll slip and stay in the same state with probability 0.1, and so 90% of the time you'll stay in the you'll end up in the state where you expected to end up. So this is V star. So basically 2.08 is V star for this initial state as 0. And you can see that the optimal policy is to go right. This means that even though the reward, the one-step reward, is negative, and we know that it could have taken the left action and received a reward of a non-negative reward of 0 to go to the sync state, after doing value iteration, it turns out that the best thing you can do is actually just incur these penalties, because eventually you'll be able to take this right reward and get a nice big bonus. And so the value from this state is 11.05. Now you might ask, why isn't it just 10? And the reason for this is because there's a probability that the agent might end up back in this state. And so then it can take the action again. So if we were to set rho to 0, the value of this last state in the chain should be 10. And let's check. And there you go. It's 10. So it's a bit more interesting when you have stochasticity. So we'll set that over here. Now the gamma also affects how much you discount future rewards. So if gamma is too small, that means that future rewards get discounted a lot more. And so it's less important to, you really want the rewards immediately. So if we set gamma to some very small value, let's say 0.1, what's likely going to happen, I hope I'm not incorrect, what's likely going to happen is that the optimal policy will switch, and we're no longer going to want to incur this penalty because the rewards just get discounted too much. And so by the time we reach this end of the chain here to receive this large bonus, this bonus will have been discounted too much, so it's not worth it, and it's better just to take the non-negative but 0 reward. And so let's see what happens when we have a small value of gamma like that. And here we go. So now we have a value of 0 from this state, which says just always take the left action because it's too expensive to wait that long. You can see that at some point it does become worthwhile. And again, this is just numerical differences. So as you play with the value of gamma, these things will change. So if we make this even smaller, we'll likely see that this is the fourth state. We'll probably want to go to the left. Let's see. Oh no, it still stays there. But you can see the values change. And again, the values are directly a function of gamma. So we're going to set gamma back to 0.95. Again, this is a typical value that we use in reinforcement learning. We use a value of gamma closer to 1. And so now we have this policy where the actions for all states are to move right. And we have this value of 11.5. And again, this is not 10 because there's a probability of staying in the same state. So you're basically adding that extra factor. Okay, so now we can do exactly the same thing, but with policy iteration. So let's see. And I think these values are all the same. So we basically come up with exactly the same solution with both value iteration and policy iteration. Again, this is not always the case because policy iteration is only interested in iterating until the policy is stable. Sometimes it might result that this means that the value that you compute is numerically accurate, but it's not required. Okay, so now we're going to be interacting with the environment and moving more into the reinforcement learning scenario. What we were doing before is more like planning, where we're solving for the full system, given that we have access to the full dynamics. So this is the step function that I was mentioning before. Um, we are going to be defining it here for this chain MDP, where given a state S and an action A, this is simply going to return the one-step reward given by a reward function R, and it's going to pick the next state given the transition dynamics B. So now we can do Monte Carlo on this chain MDP. So we're going to be setting epsilon. This is for epsilon greedy. So standard value is 0.1. Total trajectory. So this is the total number of trajectories that we'll use for the learning process. And max steps per trajectory is the limit on how long a trajectory can be. So I've chosen these values here, but you can play with these and see how the learning changes. So we'll run this. It takes a little while to execute all of these trajectories. And what will be interesting is to compare the value and the policy we get with Monte Carlo relative to what we can get with the exact methods that we were using with value iteration and policy iteration. So what we can see is that in terms of policy, we did actually converge to the optimal policy, which is to move right on every state. So we always want to move right. However, if we look at the numerical values, we can see that this first state has a numerical value estimate of 1.35, whereas we know that the true value is actually 2.08. So there is an error incurred by using these methods. And these errors come from the stochasticity of the environment, how much you interacted with the environment, and how you're updating your estimates, how you're doing exploration. All of these things affect how well your learning process proceeds. But for this particular example, we were able to find the optimal policy. It's just that the numerical values that we found, our numerical estimates of V, were not that great. And so we plot this over here. So these are the returns that we receive as we interact with the environment. So we can see that there's some stochasticity here. We can measure how the maximum difference between our current estimate V hat with the ground truth V star. And we can see that as we interact with the environment, it starts going down, 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 and then it sort of reached a plateau. So it's not able to sort of do much better than that, which you do find sometimes. And this is due to various different reasons. But it's one of the things we measure when designing new learning algorithms. And so the average gives us a similar type of dynamic. So now we're going to do Q-learning on the same chain MDP. So we're going to compare Q-learning with Monte Carlo. So for Q-learning, we have to specify alpha. So again, this is the step size or the learning rate, or how aggressively we update our estimates given the temporal difference error. Epsilon, again, is just the epsilon, the value for epsilon greedy. The total episodes that we'll use, and the limit on the number of the number of steps for each trajectory. Note that we're using a lot less episodes than for Monte Carlo. Here we're using 600, in Monte Carlo we're using like 50,000. So let's see how this does. So we'll run it here. It'll run for a little bit. And again, what we're going to be interested in seeing is the policy that Q-learning returns, as well as the numerical values. So again, we see that the policy is exactly as we'd expect. It gives us to go right everywhere. And the numerical value is actually doing quite well. So now for the start state, we have a value of 2.05, which is very close to the value that we have when we compute the values exactly. The end state, you can see that when we compute it using planning, when we have access to the full model, is 11.05. Q-learning gave us, I believe, 10. So a better estimate, this with fewer iterations gave us a much better estimate than Monte Carlo methods. And this is in general what we observe in practice. So here are iteration returns. Here we see a decaying error in terms of the maximum error as well as the average error. And so Q-learning does quite well. So that chain MDP was a very nice system to motivate and sort of illustrate the different algorithms and how they compare to each other. But as probably most of you know, the real excitement nowadays is with deep reinforcement learning. And deep reinforcement learning is combining uh, reinforcement learning with deep neural networks. And this is what has allowed companies like DeepMind to develop AlphaGo, which is a reinforcement learning based agent that beat the world champion in Go. They have AlphaZero that can also play chess better than pretty much anybody in the world. And so it combines the ideas of reinforcement learning with the expressive power of deep neural networks. And so we're going to explore this a little bit here. So the way it works, how deep neural networks are used typically in reinforcement learning is as our function approximators for Q. So previously we were maintaining estimates of Q, but they were still in tabular fashion, right? So the ground truth for Q, so the true Q star, was an array of number of states times number of actions. When we were doing Q learning or Monte Carlo estimates, we were also maintaining an array of number of states of number of actions, but those are simply our estimates. With deep networks, what it allows you to do is to use neural networks to use that as a function approximator. So you're no longer maintaining a tabular representation. So you no longer have a matrix. You now have a function where you feed it in a state S, and the function will return the values, the Q values for all actions A. And so we typically talk of neural networks as being parametrized by theta. So theta represents all the weights, all the strength of the connections in a neural network. The reason this is so powerful is that now, because we're not expressing things in a tabular fashion, we don't have to specify a priori how many states we have in our system. So for very large systems where there's a large number of states, or perhaps even an infinite number of states in continuous systems, an infinite number of states, obviously we couldn't express in a matrix in NumPy. But we can express it using neural networks, because neural networks allow us to have this general function approximator parameterized by theta, where we can obtain a value estimate for any state. Now, whether that estimate is any good or not is a different question, but we can provide for any state some type of estimate. And so what we're trying to do with deep reinforcement learning is to update the parameters theta such that our function approximator that it induces is approximately equal to Q star. So another interesting thing about this is that, as I said, it can give us an estimate for any state, even states that we've never seen before. So how well it provides a value for that is the generalizability of the network. And so we're typically interested in training networks that are able to generalize well. And so again, this is different than what we had before, where we had purely tabular methods where we have to specify we have 10 states or 7 states or whatever. But you can't provide, if somebody says, oh, actually there's an 8th state, you're out of luck, because you've basically pre-specified how many states you have. And so this idea has actually been around for quite some time, even though it was popularized by DeepMind in 2015 by using deep neural networks combined with reinforcement learning to train agents to play Atari games at superhuman levels. This idea was used already back in the day in 1992 by Gerald Tesaro, who trained an agent to play backgammon. And the paper is linked in the colab notebook. So when training neural networks, what we use are something called loss functions. And these are similar to the learning update that we had in Q learning. So if we're given a transition from a state S and action A, we receive the next state S prime and a reward R prime. The loss is very similar to the temporal difference update that we had before. So we have our immediate reward, the value of the next state, and we're taking this maximum here because we're basically trying to get V, our estimate of V star from our current estimate Q, multiplied by the discount gamma, and we're comparing this to our current estimate of Q at state S in action A. So this is exactly the temporal difference error, but now we're going to square this to make it a positive term, because this subtraction might actually be negative, and this will become our loss. And this loss is actually the heart of DQN, which is this algorithm that I just mentioned that really popularized deep reinforcement learning, and it was used for training Atari agents. So there are many other details that were actually necessary to get DQN to train properly and to learn how to play these games at superhuman levels. Those details are beyond the scope of this Colab notebook, but for those interested, there are many resources linked below that you can read to find out more. I'll go through some of the important aspects that we will be using in this Colab notebook. One of them is the experience replay buffer. So as we were seeing before, as the agent interacts with the environment, every time it interacts with the environment and receives a next state and reward, we would update our estimates of Q. Now this is fine, but it's a bottleneck of sorts, because that means that we can only update our network every time we interact with the environment. So what they did in the DQN paper is that they stored every experience that they have from the environment, every transition, they stored in an experience replay buffer. So you can think of this just as a large memory. And so then they don't actually do the learning process or the training after every transition. What they do is once they've filled up the replay buffer beyond a certain limit, they will be sampling batches. So these are batches of transitions and doing learning on those batches. So the reason this is useful is because using modern hardware like GPUs or nowadays TPUs, we can use this hardware to train on large batches of data very, very efficiently, much more efficiently than on CPU with a single transition. It also allows the agent to potentially distribute the training. So you can have multiple agents interacting with the environments and collecting information to store in a large experience replay buffer, and then we can learn from this collective experience. So at each point when the agent is learning, it's no longer learning from a single transition, but it's learning from a batch of transitions. So we express this using this expectation. So we're going to be sampling uniformly from this experience replay buffer and performing the temporal difference learning update, or computing the loss based on this temporal difference update from this set of sample transitions. Okay. So some final implementation details. Again, we're using Dopamine, which is this reinforcement learning framework that we released 2 years ago. Dopamine provides both TensorFlow and JAX implementations of the DQN network. We're going to be using the JAX implementation. We also have JAX implementations of the replay buffer, or it's compatible with the replay buffer. Sorry, is compatible with both JAX and TensorFlow. And we have setups for running a full experiment. So that's interacting with the environment, sending the parameters to the agent, running the training step, collecting statistics about how well the agent is performing. All of that is provided by Dopamine to make it easier to run these types of experiments. So we're going to be running on a classic control example. Training an Atari game is very expensive. It takes about 5 days on a modern GPU. So we don't have time to do that here. Cart pull is a nice example that's been around for a while, as I already introduced it before, where we have this black cart that's trying to balance this pull, as it's doing here. And so we're trying to teach the agent how to do this. And the agent, the actions it has is it can move the cart left or right. So OpenAI Gym provides this environment that we can import, as I show here. And so the main API methods that we'll need from the Gym environment are step, to step in the environment, reset the environment, and to render, because we'll be rendering videos of our trained agents. So this is going to simply load the cart pull environment from OpenAI Gym, and we're going to render a starting state, as we see here. Okay, so we're going to be animating, as I mentioned, so we just need to run the cell. You don't need to worry about what it's actually running, but you can double click to look at it if you're interested. And so first off, we're going to start with what's called a blind policy. So this is a policy where it doesn't matter what state you're in, you're always going to pick the same action. And so this is, as you imagine, it's a very terrible policy. So this is the only left blind policy. So it doesn't matter what state you're in. As you see, it's unused. We're always going to return 0, which is the action to go left. It doesn't matter where you are. So we're going to run this in the environment, and we're going to animate how well our agent performs, so we can see the effects of our learned policy. So we'll animate it here. Play, and you can see that because as expected, it always goes left, and the poll falls pretty quickly. On the right here, we're plotting the returns that the agent is receiving. So you can see, as I mentioned, in cart pull, you receive a reward of +1 for every step that the poll is balanced. And so initially the poll starts off balanced, so you receive a reward of +1, but very quickly the poll goes beyond the threshold of the angle that's allowed to receive a reward of +1, and so from that point onwards the rewards flatten out, the returns flatten out because the agent is no longer receiving any more +1s. Okay, so that's a pretty bad policy, as you would expect. So what we're going to do is we're going to be training an agent to perform better with dopamine. And so we'll be using a neural network. It's not super deep, but it's somewhat deep. Again, we're going to be using JAX for this, and this is the code of the network that we use. All of this is already implemented in dopamine, but I just put the code here so that we can go through it together. So the way it works is we're going to be extending the Flax, which is a library built on top of JAX, the Flax module with our network. And so what we have to override is the apply function. So apply will receive a state X and the number of actions because the output of the network is going to be, again, the Q estimates for each one of the actions. So we have to specify how many outputs we want. So this is basically how we're going to initialize the network. And it's using the Xavier initialization, which is a standard initialization for neural networks. Here, this is, you don't have to worry about too much. This is a technical detail with Flax, where we're dealing with when we're dealing with batches, we need to do this little trick so that we can write the code in an optimal way. We're going to be, this line is simply casting it to floats. This line is simply flattening the inputs out, because sometimes you may receive multi-dimensional inputs. So for instance, if you're dealing with an image where you have X and Y for the different pixel coordinates, and then you may also have RGB channels. So this might be a multi-dimensional matrix. We're going to be flattening this out. And now what we're doing in these lines is we're simply normalizing the values of our inputs so that they're in the -1 to 1 range. And this is just to make it easier for the learning process. This is a kind of standard trick that we use in training networks. Not always, but it can often help. Okay, so here we finally start getting into the network. So we're going to pass our input X through a dense layer. So that means that all of the input neurons are connected to all of the output neurons of this particular layer. We're specifying that the output of this layer is going to have 512 units. So that means that whatever the dimensions of our input, they're going to be connected to 512 neurons, and we're going to connect all of those possible pairs. And we're going to save that again in X. We're going to do what's called a rectifier linear unit, and this is basically a way of scaling the outputs of your networks. And again, this is to help with the learning process. I won't go into details here, but there's extensive literature available for that online. And then once we have that, we're going to again pass it through a dense network of dimensions 5 to 12. And then after we've done that, we're going to pass it through one final dense network where the output is going to be the number of actions. So this is essentially a 3-layer network where the first 2 layers have 512 hidden units, and the last layer has the number of actions. So it has the number of actions because that last layer is going to be our estimate for the Q values, and that's what we're going to return. Okay, so this cell over here, which we're going to run, this creates a dopamine DQN agent using the cart poll network. And so we use this library called ginconfig, which allows us to do Python injection, which is quite nice. What that means is that I can specify for this object, these are the constructor parameters that I want to use. So we're going to use a gamma of 0.99. You don't have to, this is for the replay buffer, but we don't have to worry too much about this. One thing that's interesting is we're using the epsilon greedy exploration strategy that I mentioned before. And it's called identity epsilon because, as I mentioned, you sometimes might want to decay the value of epsilon, but in this case, we're going to maintain a constant epsilon throughout training. The rest of the parameters are beyond the scope of this colab notebook, but basically the optimizer we use to train the network and some parameters for the experience replay buffer. So this line is basically doing this injection that I just mentioned. So it's setting all these parameters. And in this line, here's where we're creating the agent. So again, if you want to find out more details about what's happening under the hood, you can check out the dopamine repo, which is linked in the notebook. It's open source on GitHub. And now we are going to try to train this agent. So the first thing we'll do is we are going to take the agent with the initialized network, so it hasn't done any learning yet. So we just initialize the network, and so because the network is initialized, we can actually get an estimate of Q, and we can use this to interact with the environment. Because it hasn't learned anything, it's probably going to be a pretty bad policy, but it likely won't only pick the left action like the blind policy that we were looking at before. So let's look at how this does. It actually ended up picking only right. If you run this multiple times, you'll likely get different types of policies. Again, the agent hasn't learned yet, so the network is able to give you a value estimate, but it's just not very good. And now we're going to train the agent. So again, I provide some, I'm going to start it already because this takes a little while, but I have some sliders here that you can play with. If you double click, it makes it easier to play with the sliders. So max steps per episode, again, is this cap on how long a trajectory can be. The training steps, this is how many training steps we're going to train the agent for each iteration. So basically, we will be training the agent for 30 iterations, and each one of these iterations will have at most 1,000 training steps. And each of these training steps will be executing a trajectory that might end, for instance, when the pole falls beyond a certain threshold. And so, but it might not, right? So if the agent has learned how to balance the pole, it might stay balanced for a while. We don't want to say it to stay there forever, because that might mean that the agent doesn't learn other things that it might need to learn. So we're going to set a limit on how long a trajectory can be, and that limit is 200. And so the agent is training right now, and so we're printing out for each iteration, which again consists of multiple training steps and potentially multiple episodes. We're plotting the average return. So we can see that when it starts off, when we had this bad policy here, we can see that it sort of capped off at 11 reward. So it was able to stand for 11 steps. And we can see that on average, in the first iteration, it can stand for 10 steps, but we can see that it's quickly making progress. And so the maximum, because we're setting the max steps per episode to 200, the maximum accumulated reward it can receive is 200. One thing you might notice is that we're not actually applying a discount factor when we're measuring this. So when we're reporting the returns, we often don't include the discount factor. We just sum over the reward. So the maximum reward the agent can receive is 200, which we can see it received here. There's a little bit of instability as it goes back down, but the agent is still learning. And we can see that by iteration 16, it's pretty much staying pretty stably at 200. Now, why doesn't it stay at 200 forever? The reason for this is that there is some stochasticity in the transitions, and there are issues with this network when you train it, that sometimes you can have problems when you overtrain a network, and you can sort of reduce the performance that you were having before by performing too many updates. And so this can be leveraged by changing, for instance, the epsilon rate, or changing the learning rate that you use in your optimization. But these are beyond the scope. We've still managed to get an agent that performs much better than what we had before. And so now we're going to animate that here. And so this is using the policy that is now a result of the training process that we just executed. And so this is taking a bit longer because the agent is actually performing pretty well, we hope. So let's execute this policy. So we can see now the agent is performing pretty stably. Even though it's sliding to the right, the pole is still within the threshold of what we'd want. And we can see this reflected in the cumulative rewards, where we no longer see it flatten out except until the very end. So again, had we stopped the policy, the training process at, say, iteration 22, we'd likely see the pole balanced forever. And again, these are some of the things that you have to deal with when training these things, figuring out how to do early stopping if necessary, or how to update your training regimen so that you don't start seeing this decay that happens, that sometimes happens as a result of too much training without updating your parameters accordingly. Okay, so that brings us to the end of this lecture. I hope you found it useful. I hope these things were clear, and we should have some time for some questions so I can address any of those. I wanted to mention these resources that I provide at the end of the notebook that you can refer to if you want to read more about this. There's the canonical reference for RL, the Sutton and Bartow book that I highly recommend. the OpenAI blog, the dopamine repository, which we used for the last DeepRL example, the paper for TD learning with to play backgammon, and the Atari paper by DeepMind where they introduced DQN. Okay, so I hope you like this. If you have any questions or comments, probably the best way to contact me is via Twitter. I'm pretty active there. Um, I hope I see many of you in future conferences discussing new ideas for reinforcement learning, or seeing how you're applying reinforcement learning to your projects. Let me know if you have any questions, and happy to chat. Thank you very much.